All right, so tonight we're going to talk a little bit about op amps. Before we get into that, I just wanted to say a word about midterms. I have graded your midterms, but I left them at home, so I'm not going to go over a review of the midterms until next time when I have them to give out. So you can check your grades online; they should be there, but I'm going to review them next time. Okay? So we're going to talk a little bit about op amps tonight. We've already talked a little bit about them in 302, so you guys might remember a few things about them there, but we're going to go into more depth tonight, and we're actually going to continue talking about them next time. So we're going to do an introduction now, and we're going to talk about two circuits that use op amps, and then next time we're going to talk about 3 more circuits that use op amps. Okay? So these are very versatile chips, and we'll learn a little bit about how they work over the next couple of lectures. The lecture after that is actually talking about comparators, which have some similarities to op amps as well. So we'll sort of extend our knowledge there too. So tonight we're going to talk a little bit about what op amps do, basically the fundamentals, the basic purpose of them. We're going to talk about how they do that, what's inside them that makes this happen. Then we're going to get on to how we actually use them and analyze them. And we're going to talk about 2 circuits in particular tonight. We're going to talk about an inverting amplifier and a non-inverting amplifier. These are both circuits that use the op amp chip, the operational amplifier chip, as their centerpiece, the sort of the heart, the thing that does all the work. But they're 2 different circuits that use that chip. So we'll talk about that. And then we'll go on and do a preview of tonight's lab. Okay? Any questions before we get started? Okay, cool. So let's talk about what op amps do. So, bless you, the fundamental purpose of operational amplifiers is to take small signals and make them bigger. They're amplifiers, right? That's the purpose of an amplifier. It takes a small signal and it makes it bigger. So this is an operational amplifier, so that's what it does. We can use them as voltage amplifiers or as current amplifiers. The circuits that we're going to be talking about tonight are primarily used for voltage amplification, but tomorrow, or on Thursday, we'll be seeing a circuit which is primarily used for current amplification. Okay? So you can use the same chip in different ways. Okay? So the chip itself is fairly small. It's like this big. You can actually get some that are even smaller that can be mounted on the surface of a printed circuit board. But they're a little bit harder to handle, harder to pick up. You can't put them in a breadboard, so we're using chips that are this big. Okay? But despite the small size of this chip, there's actually quite a lot of things going on inside the chip. So let's talk about that for a minute. Let's talk about what is actually inside them that allows them to do this amplification work for us. Could somebody hit the lights in the back for just a second?
Back here? No, that's fine.
Okay. So I'm going to pull up a diagram of what's going on inside of the op amp. And you should, so it's made up primarily of transistors, and you should see some parts that you recognize from the amplifier circuits that we've already made ourselves with transistors. Okay? So all of this is inside of one of those little chips that I showed you. Okay? the inputs come from the left-hand side here. And what happens is that you've got these two series of transistors that are vertical. They're sets of 3 transistors here and here. One input is connected over here, and the other input is connected over here. Together, these two sets of transistors create something called a differential amplifier. So it takes the difference between these two inputs, and it amplifies that difference. Okay. Then the output of that circuit comes over here to this little part which is outlined in magenta. And you might notice this configuration here where you have the signal coming in and connected to the base of this transistor, and then the emitter of that transistor connected to the base of the next transistor. Do you remember what we call it when we have 2 transistors configured like that? That's right, a Darlington pair. So you guys remember that that is a configuration which provides a very, very large amplification from the input current to the output current, right? So you know a little bit about that. And now, if you had, so the output comes from the collector of this final transistor. So if you have the input signal going to the base of a transistor, and then the emitter connected to ground through a resistor, and then the output coming from the collector, do you guys remember what type of amplifier that would be? Yeah, it's a voltage amplifier. This is a form of a common collector amplifier. Or, I'm sorry, a common emitter amplifier. I said that backwards. Common emitter amplifier, right? The emitter is connected to ground. So this is a voltage amplifier, and it's using this Darlington pair. So this is a very high gain voltage amplifier. And then the output comes here to this set of transistors, which is in a push-pull configuration, right? A CMOS configuration. You've got this transistor up here and this transistor down here working together so that you can set the output level to whatever you want. So obviously there's a lot of other things going on here. We're not going to get into the details of exactly what's going on in every single case, but you guys have a little bit of a feeling of what's going on. We take the inputs, we amplify the difference between them, and then we amplify that voltage even more, and then we send that to the output. And this CMOS configuration allows us to have a decent amount of current coming out of the output. Okay? So, so that's basically what's going on inside of an op-amp. Okay? Questions about that? Okay. Then could somebody turn the lights back on? So,
Lots of transistors.
lots of transistors. Yes, that's the takeaway. Lots of transistors inside them. The good news is that you don't have to understand all of that stuff in order to use op-amps. Okay? Op-amps are very useful because they sort of abstract all of those complicated circuits inside, and you don't have to think about any of that stuff when you're building op-amp circuits or analyzing somebody else's op-amp circuits. Okay? So if you look at an op-amp, the diagram for an op-amp looks like this. It's got a negative side and a positive side, and then an output. So these two terminals on the left-hand side are the inputs. This is the inverting input. This is the non-inverting input. And this is the output. In order to make the op amp actually work, you also have to connect power, or positive voltage and a negative voltage. But oftentimes, the positive and negative power supplies are not shown, just to make the diagram a little bit cleaner. Okay? So, the good news is that when you're analyzing op-amp circuits or designing your own, there's really only two rules that you have to remember. And if you can remember those two rules, then you can understand how just about any op-amp circuit works. Okay? So let me tell you what those rules are. First one is that the non-inverting voltage is equal to the inverting voltage. Basically, the voltage at your two input terminals is the same. Okay? And the second rule is that no current flows into the inputs. Okay? If you can remember those two rules, then you can analyze just about any op-amp circuit that you want and understand how it works. Okay? So let me give you an example. We're going to have, so this is an example which is the inverting amplifier. Okay? So this is the first circuit that you're going to build tonight.
That's the inverting amplifier.
Yeah. So this is so let's say that this resistor right here is 1 kilo ohm, and this resistor here is 10 kilo ohms. Okay? This resistor is called the input resistor, or Rin, and this resistor here is called the feedback resistor, or RFB for short, because it feeds back some of the output to the input. So let's say that you had 2 volts right here at the input to this whole circuit. Okay? And now let's use the 2 rules that we know to try and figure out what the output voltage is going to be. Okay? So we know that we have 2 volts here. We can use rule number 1 to tell us what the voltage is going to be right here at our inverting input. Right? What would that voltage be right there? Well, not quite. We have 2 volts on the left side of this resistor, but let's look at our other terminal. our other terminal is hooked straight to ground, right? So we know that that is 0 volts right there, right? So if we know that we have 0 volts at this input to the chip, what voltage do we have at the other input to the chip?
0 volts.
0 volts, exactly. So that's from rule number 1. We know that. So now we have a 1 kilo ohm resistor with 2 volts on one side and 0 volts on the other side. Can we figure out how much current is flowing through there? Well, it's not 0, right? We have a voltage across the resistor, so we can use Ohm's law, right, to figure that out. So we say I equals V over R. So in this case, the voltage is the voltage difference between the two sides of the resistor. So that would be 2 volts minus 0 volts, or just 2 volts, over our resistance, which is 1,000 ohms.
2 milliamps.
Yeah, so that comes out to be 2 milliamps flowing through there. Okay? So we have the left-hand side of the resistor more positive than the right-hand side. So we have 2 milliamps flowing from left to right there. Okay? So now, how much of that current is going to flow into the chip?
0.
None. That's exactly right. That's what our second rule tells us, right? No current flows into the inputs. No current flows into the chip. So the only other place for that current to go is up and over here and through our other resistor, right? So we know how much current is flowing through this other resistor?
2 milliamps.
2 milliamps, exactly. So we have that flowing through there, and now we have 2 milliamps flowing through 10 kilo ohms. We can use Ohm's law again, right, and figure out the voltage. So here we say V equals I times R. So that is 0.002 amps times 10,000 ohms. So how much voltage is that? It should be 20 volts, right?
Would it be, would it be positive? 1 volt?
Good question. So it's a difference of 20 volts, and it's flowing from left to right. So the way that I'm drawing it, the current always flows from positive to negative. So that means that the left-hand side has to be positive, and the right-hand side is 20 volts more negative than the left-hand side. Okay? Now we know that the left-hand side is at 0 volts, right? And then we go down by 20, so our output voltage has to be minus 20 volts. Okay? So we just use these two rules, and only these two rules, well, plus our knowledge of Ohm's law, to figure out how this circuit works, right? And if you guys remember back to 302, this is very much like the circuit that was at the middle of your fiber optic transmitter. So this is the circuit that took the signal from your voice and amplified it before it got sent out as light. Okay, so now you know a little bit more about how that works. So we used these two laws to figure out what was going on with this circuit. But it turns out that if we see a bunch of these inverting amplifier circuits over and over again, it can be kind of tedious to work through the equations every time and do the analysis. So we also have a shortcut that works with inverting amplifiers. Remember, these two rules will work with any type of circuit that you have. But if you know that it's an inverting amplifier, you can use a shortcut to get the answer a little bit quicker. Okay? So with inverting amplifiers, we say V out equals V in times R feedback over R in. Okay? So we can do that for this specific case and make sure that it works, right? We say V out equals V in, which is 2 volts. Oh, and then, yes.
That's inverting, right?
Thank you. So very importantly, we have to have this negative sign. So it would be minus 2 volts times our feedback over R in. So that's 10 kilo ohms over 1 kilo ohm. So that comes out to be 2, or minus 2 times 10, so equals minus 20 volts, right? So this formula, you can see it checks out with the inverting amplifier that we have. Okay? So this is one type of amplifier that we can build with an op-amp. Okay? Any questions about the inverting amplifier or about the rules or anything like that? Yeah.
I noticed the little branch at the bottom has a negative V.
Yes.
You didn't give that a value or anything?
Right. So that's a good point. So, so this is the power that is supplying the energy to the chip. The power supply that we use, it determines how big the output can be. Okay, the output can never be bigger than the power supply that we're using. So it's important to choose your power supply voltages in such a way that they allow you to get a signal that's as big as you want. So if you know that your signal, you want your output to go between minus 10 and 10 volts, you would want to choose power supplies that were bigger than that. So like minus 15 and plus 15, something like that. Okay. If your output exceeds your power supply voltage, then what happens is you get something called clipping. Okay. So basically the tops and bottoms of your signals get cut off when they try to go above these power supply levels. Okay. So you can, the chip can work with different power supply levels. You just have to pick a level that's appropriate for the application that you're using. Okay. Yeah.
Are there multiple variations? This is the 741. Are there multiple variations that are kind of rated for different like minimum, maximum voltages, or how is that?
Yeah. So yeah, that's a good question. So these rules apply generally, and this formula applies generally for any op-amp chip, right? Any chip that calls itself an op-amp. But like you say, there are many flavors of op-amp. So so the 741 in particular has a positive and a negative voltage supply. There are others that have just a positive supply and ground, so some do that. Some chips are rated so that your output can go very, very close to the supplied voltage levels. They call those the rails, so they say that those chips, the output can go rail to rail. Other chips, like the 741, have sort of a buffer zone between the power that you supply and the output voltage that you get. So you could have a supply of maybe 15 volts and the output can go maybe plus or minus 12 or something like that.
Is that's we're losing because of the diodes inside, right?
Yeah, it's because of the internal circuitry. I don't know enough to say exactly which components they are.
Sorry, the transistors inside.
Right. Yeah. But because of the way that the internal components are set up, the output can't go quite all the way to the supply voltages. So again, depending on which application you're building, you can choose a chip that meets your needs. And as long as it calls itself an op-amp, you can still analyze it using these rules and these formulas that we're learning today. Okay. Yeah?
So is there an assumed like positive voltage on the other side of this one?
Yes, yes. There is an assumed positive voltage. Generally, you either write both the positive and the negative voltage, or you leave them both off. I got a little bit sloppy and just erased the one when I was doing the other part of the circuit. So you can see it both ways. You can see it where the positive voltage and the negative voltage are written in, but oftentimes they are left off because the other circuitry gets in the way. Yeah. So, other questions? Okay. So this is an inverting amplifier. And it's called an inverting amplifier because the output voltage is of the opposite sign compared to the input voltage. So if you have a positive input voltage, you get a negative output voltage, and vice versa. So this amplifier inverts the sign of the voltage. Okay. So let's talk about another one, another type of circuit that you can build, which is a non-inverting amplifier. Okay? So again, it's an op-amp, so we can use these same two rules because they apply to all op-amp circuits. But the way that the circuit is built is a little bit different. So we'll have to look at them again. So with the non-inverting amplifier, it's constructed in a similar way, but the inverting input now goes to ground through a resistor, and then the input to the circuit comes from the non-inverting input to the op-amp. Okay. All right, so this is the input to the chip now, and the output is there. So let's say that we had a positive 5-volt input, and we want to figure out what the output voltage is. Well, we can use these two rules to figure that out again. So let's give that a try. So we know that we have 5 volts at the inverting terminal of the chip. So what is going to be the voltage at the non-inverting?
5.
Thank you. They're both the same. I said it backwards. We have 5 volts at the non-inverting, so we have 5 volts at the inverting terminal as well. Okay. So we have 5 volts on this side of the resistor, the input resistor, and we have what voltage on the other side? 0 volts, exactly. So we have a 5-volt difference across this resistor. And we know that that resistor is 1 kilo ohm, so can we figure out how much current is flowing through it? Yeah, 5 milliamps, right? If you have a certain voltage across a 1 kilo ohm resistor, then the current is just that many milliamps, right? So we have 5 volts, so we have 5 milliamps. Now, this time the voltage is more positive on the right-hand side of the resistor, and it's lower on the left-hand side. So that means that the current is going to be flowing from right to left here. Okay? Right? We have 5 volts on the right-hand side, 0 volts on the left, so the current is going to flow from right to left. How much current is flowing into the chip? None, exactly. That's what Rule 2 tells us. So we have no current flowing into or out of the chip. So that means that how much current is flowing through this resistor up there?
5 million.
5 milliamps, exactly. Right? It's the same. There's only one path for the current to flow down, so it has to be the same. So now we've got 5 milliamps flowing through 10,000 ohms. So we can figure out the voltage across that resistor, right? V equals IR. So it's 0.005 amps times 10,000 ohms. So that's 50 volts, right? So now we can figure out the output voltage. Now this is kind of tricky, right? You might sort of jump ahead and say, oh, well, it must be 50 volts, right? But be careful, it's not 50 volts. Anybody tell me what the output voltage is? Well, we have 5 volts over here, and then we go up by another 50 volts. So what is it? 55, exactly. So the output voltage is 55 volts. And that's positive, right? We started at plus 5 volts, and then we went up by another 50 volts, so it's plus 55 volts, okay? So we used these two rules, and we were able to figure out what was going on in a non-inverting amplifier circuit as well. Okay? Now, just like there was a shortcut formula that we used with the inverting amplifier, there's also a shortcut formula that we can use with the non-inverting amplifier. So if we look at a diagram and we see that we have a non-inverting amplifier, we can use this formula. We can say V out equals V in times R feedback over R in plus 1. Okay? So we can try that out again in this case and see that it, make sure it checks out. So we can say that is, our input is 5 volts, right? That's what we said over here. So that's 5 volts. And then our feedback is 10 kilo ohms. And then our in is 1 kilo ohm. So all that plus 1. So this is 5 times 10 plus 1, so 5 times 11, right? So our output voltage is 5 times 11 volts, or 55 volts. And you'll notice that there's no negative sign here, right? The output voltage has the same sign as the input voltage. So we say that this is a non-inverting amplifier because it does not invert the sign of the voltage. Okay? So, any questions about that? Okay. So, So those are the two types of amplifier circuits that we're going to build tonight. There are other types that we're going to talk about next time. But in general, you can see that as long as you remember these two rules, you can analyze any op-amp circuit that you want. And once you do that, you might also find that there are other formulas that can help you do the analysis a little bit quicker. But if you can't remember all of these formulas, you can always go back to these two rules. As long as you remember those two rules, you can figure out what's going on. Okay? Okay. So, so that was really what I wanted to say for the lecture. So let's talk briefly about the lab. Let's just do a quick preview of the lab. Really, the main thing that I wanted to say about the lab is that, well, first of all, I wanted to show you guys how to kind of translate what we're doing up here on the board to what's happening inside the op-amp. Okay? So up on the board here, we're drawing these triangles, and we've got the input and the output, but in your lab, you're going to be working with these rectangular chips that have 8 terminals on them. So let's talk about how we can kind of translate from one thing to the other. Okay? So the little op-amp chips have 4 terminals on each side. So let's talk about how those terminals relate to the diagrams that we're doing up here on the board. Okay? So the terminals are labeled in the same way that all chips are. Terminal number 1 is the top left, and then the numbers count down the left-hand side, and then they wrap around in sort of a U shape, and they continue up on the right-hand side. Okay. So really, what's happening is that the op-amp is laid out sort of like this. It's got terminal 2 is the negative inverting input. Terminal 3 is the non-inverting input, and then terminal 6 is the output. Okay. Terminal 7 is the positive supply, and terminal 4 is the minus supply. Okay? So if you want to sort of figure out in your brain how to go from the diagrams that we have up on the board to working with the chip, you could sort of visualize it this way. Okay? The only other thing is that I wanted to remind you guys that when you put this chip on your board, you should put the chip in the middle of the breadboard so that half of the legs are on one side of the board and then the other half of the legs are on the other side. So you can put the chip sort of like this in the middle, and you've got the pins sticking out both sides. And the key is that the left-hand side is on the left-hand half of the board, and the right-hand legs are on the right half of the board. Okay? If you put the chip, say, over here, then the terminal 1, for instance, is going to be connected to terminal 8, right? Because the connections in a breadboard go side to side like this. So, so do not do this. Make sure you put it right here in the middle of the board so that half the legs are on the left of the board and half the legs are on the right. Okay? Yeah.
So there's like 3 unused terminals in this chip?
Yes. So that's a good question. So we haven't shown any use for terminal 1, terminal 5, and terminal 8. Terminal 8 is truly disconnected. It's not attached to anything. Terminals 1 and 5 are used for something called an offset null. Okay? If you were using the op-amp for really high precision circuits, then you could attach a little potentiometer between terminal 1 and terminal 5, and you could dial it in and do a little bit of fine tuning. But that's only for really high precision stuff. We're not going to worry about it. So it's not going to be used at all tonight or in any of the labs that we do. So, yeah, good question. Other questions? Okay, so then let me take roll and I'll let you get started on the labs.